The mechanism of polymerization used in the synthesis of polymers allows for the classification of the latter into two major classes, namely, addition and condensation polymers. In addition, polymerization, also called chain reaction polymerization, monomers are added together with their structure unchanged. This polymerization technique consists of three steps: initiation, propagation, and termination. On the other hand, in condensation polymerization or step growth polymerization, monomers or oligomers react with each other to form larger structural units while releasing smaller molecules as a byproduct, such as water, methanol, or carbon dioxide. The technique used for the synthesis has a substantial impact on the polymer's properties, since an addition polymerization technique usually polymerizes a homopolymer. In contrast, a copolymer is usually synthesized by a condensation polymerization technique. Besides the kind of polymer, according to the polymerization technique, we can have linear, branched, and network polymers. The key difference between linear and branched polymers is that linear polymers have a linear structure without any branches, whereas branched polymers have a branched structure. Another essential feature is that a polymer can be modified. In other words, producing a new functional polymer from a reactive polymer precursor is possible. This procedure is called a post-polymerization modification. An example of this is the vulcanization of natural rubber using sulfur or the nitration of cellulose. Further, regarding the polymer composition and whether it is a homopolymer or a copolymer, we have to keep in mind the polymer's configuration sequence through its relative stereochemistry of adjacent chiral centers within the polymer. This relative stereochemistry refers to the term tacticity. For polymers, we can find mesostructures. According to IUPAC, mesostructures are relative configurations of consecutive, but not necessarily contiguous, constitutionally equivalent carbon atoms that have a symmetrically constituted connecting group, if any are designated meso or racemo, as appropriate. Thus, if the relative positions of the substituents are always the same, from asymmetric center to asymmetric center, along the length of the chain, the polymer is said to be isotactic. In comparison, an alternating configuration is called syndiotactic. These two arrangements commonly depend on complex steric constraints and require specialized reaction conditions and methods to be realized. However, for many systems, no such conditions apply, and the polymer produced is atactic, meaning that the substituents are randomly arranged, and there is no regularity along the chain. So here, we can compare the same polymer, polyphenylene, but with a different configuration. However, why is tacticity an important property to keep in mind? Tacticity affects the physical characteristics of the structure in terms of crystallinity. Crystals have regular structures, and polymers that are isotactic or syndiotactic will be able to solidify into crystalline or semi-crystalline networks. In contrast, atactic polymers have a random arrangement of the repeating units, so they will not be able to form crystals and will usually form amorphous glasses instead. When polymers have a crystalline structure, the intermolecular forces of attraction are at a maximum, so the polymer created is denser and stronger. Tacticity and crystallinity are essential in the polymer synthesis industry. Different polymerization conditions, such as temperature and choice of solvent, will affect the tacticity of the polymer formed. If a polymer of high strength is required, there is a need first to create isotactic or syndiotactic polymers. If rubber is required, there is a need to use tactic polymers instead. Therefore, there is a need to match the polymerization conditions to the type of polymer that is required. Now back to the polymerization techniques. As was mentioned, there are two main techniques: addition and condensation polymerization. In step reaction or condensation polymerization, stepwise reactions involve two different types of D-functional monomers or end groups that react with one another, forming a chain. For example, here, we can see the direct reaction of an amine with a carboxylic acid to form an amide with water as a byproduct. Once the reaction occurs, it keeps going until no further monomers and reactive end groups are available. Another example is the formation of nylon 6,6, a common polymeric clothing material, involving one each of two monomers, hexamethylene diamine and adipic acid, reacting to form a dimer of nylon 6,6. In brief, the polymerization reaction occurs between the functional groups of molecules, as it can see either A or B to form D. In step growth polymerization, one or more types of monomers can be involved, and each monomer should have at least two sites for bonding. For polymerization with more than one type of monomers, for example, involving A and B monomers, a B-step growth polymerization or a B step growth polymerization can occur. For example, the formation of polyurethanes is an example of step growth polymerization that proceeds without eliminating any molecule, therefore not following the route of condensation polymerization. In the case of polyurethanes, the functional groups are the isocyanate group and the hydroxyl group. To conclude, both the size and the number of polymer chains are dependent on the conversion degree. The growth of molecular weight in chain growth reactions is almost instantaneous, with high molecular weight polymers seen right from the start of the polymerization reaction independent of the conversion level. High molecular weight polymers are only formed after high levels of conversion, more than 98% and almost at the very end of the reaction. The rate of disappearance of the monomer in step growth reactions can be as fast as or even faster than chain growth reactions. The difference in the two mechanisms lies in the time required for the growth of a polymer chain. As the primary objective of polymerization is to produce polymers that will perform consistently and acceptably in specific end-use applications, it is necessary to control the reaction. The polymerization reaction can be controlled with temperature, pressure, or a catalyst. Some examples of polymers formed by step reaction or condensation polymerization are polyester, polyamide polyurethane, polysiloxane, polyethylene terephthalate, polyether ketone, polyether. In addition, polymerization, sometimes called chain growth polymerization, a chain reaction, adds new monomer units to the growing polymer molecule one at a time through double or triple bonds in the monomer. The polymerization process takes place in three distinct steps. First, the chain initiation, usually employing an initiator, which starts the polymerization process. The reactive initiation molecule can be a radical, free radical polymerization, cation, cationic polymerization, anion, anionic polymerization, or an organometallic complex, coordination polymerization. The next step is chain propagation. A monomer adds to the chain, and each new monomer unit creates an active site for the following attachment. Finally, the radical, cation, or anion is neutralized in the chain termination step, stopping the chain propagation. The simplest type of addition polymerization is free radical polymerization, in which a polymer is formed by successive addition of a free radical building block. A free radical is a molecule with a free electron that can be paired with an electron from another molecule. Using the following example, the three steps of polymerization could be explained as follows. Chain initiation. In this phase, the chain is initiated by a free radical R**, which creates a free radical building block. The initiation phase usually involves monomers with a double or triple bond, unsaturated carbon-at-carbon. The chain initiation phase starts when an external initiator disintegrates into a reactive group, free radicals are asterisk, and stimulates the double bond of the monomer to open up, creating a molecule with an unpaired electron or active center, 3. The period represents the active center with a free electron that got transferred from the radical to the monomer, making the monomer as the new radical. Chain propagation. In this step, the free radical building block of the monomer reacts with other monomers to create a larger free radical building block in order to stabilize the active centers. The free radical building block bonds with neighboring monomers, extending the length of the chain. The polymer chain is thus constructed by a series of addition reactions between the active center of the growing chain and available monomers. The reactive group can attach at either end of the growing chain. Each new monomer unit addition creates an active site for the following attachment. Chain termination. In this phase, the process of chain growth terminates, stops. Fundamentally, the addition process will continue until all the monomers in the system are consumed. Controlling the supply of the polymer monomers could control the total chain length. However, the chain growth usually stops by direct combination or disproportionation. Direct combination occurs when the chain growth is stopped due to combining free electrons from two growing chains and creating a single chain. Disproportionation occurs when an impurity reacts with active groups and terminates the chain growth. To avoid termination due to impurities, clean environments are needed to perform these reactions.